Now let us look to some optimization of these bare bone algorithms that we just presented. The first thing that you have to learn is that paxos, or abortable consensus, as we just presented, has one necessary condition. What is the necessary condition here? Is that an acceptor rejects an accept request with N and V if he has already answered a prepare M that is higher than N, because he has promised now not to accept any proposal less than N, i.e., if you remember, prepare extract promises to reject lower accepts. But if we just keep this bare bone rejection, we get a number of unnecessary messages, and let us see how we get that. So here is a possible scenario. We have proposers A, B, and C, and acceptors P1 to P3. So here the first case, proposer A, send a prepare with around number 80. That's fine. It gets acknowledged by the acceptors. Then proposer B sends a prepare message with proposal number 10. 10 is less than 80. So the promise done by the acceptors here is not to accept any proposals less than 10. But the acceptors have already promised not to accept any proposals less than 80. So whenever the second proposer B starts his accept phase, he will of course get rejection. So the acceptor could have already at this stage notified B that his proposal will not get accepted. So as we said here, accept 10 will be rejected. So why answer this prepare 10? You can send a negative acknowledgement, or you can just avoid it completely. So no point of answering a prepare 10 if accept 10 will be rejected. And in this was a specific case. So in the general case, no point of answering prepare N if accept N will be rejected. So here is the first optimization. Reject prepare N if, as an acceptor, you already answered prepare M and M is larger than N. So prepare extract promise to reject lower prepares. Now let us look to the next optimization opportunity. Here we have, again, 7 acceptors and a number of proposals. In this case, first A send a prepare 80, B sends prepare 90. Now, B starts his accept phase, and at this stage, as you can see here, red, which is proposal 90, is chosen by B4, B5, B6, and B7. Now A starts his accept phase, and of course, in this case, as you can see, A will be rejected only by B4 because B4 promised not to accept any proposal less than 90, so it will be rejected here, as you can see. But it will be accepted by B5, 6, and 7 because there are no promise issued by B5, 6, and 7. So this gives an opportunity of optimization again. So you can see this accept 8 blue can anyway not get a majority, as B2B, which is there's a majority of acceptor now, a value is chosen. Every higher proposal issued would have the same value. So this phase is unnecessary. So what can we do? Now we can have this extra optimization, which says reject and accept NB if you already have answered and accept MU with a higher proposal number. So an accept extract promise to reject lower accepts. So as you can see here, this accepts should be rejected. Now, one more thing that we have to take care of is to take care of what's called unnecessary messages. So normally when you do a prepare phase, it's very much like when we did in shared memory. So here you get an OK, and then you do an accept phase, you get an OK from a majority. But some of the messages here from the prepare phase are coming late. And these messages should be, of course, ignored. These are old responses. So here are all the optimization again that you can do. Reject prepare n if you already answered of a higher prepare. Reject and accept n if you have already answered with a higher accept. Reject a prepare if answered already accept with a higher number. And then ignore all messages to proposal that got a majority. Now finally, if we want to use the algorithm in the fail recovery model, some part of the state of the acceptors have to be stored in a persistent store, so that when the acceptor comes again, he remembers what his promises were. So each acceptor has to remember the highest proposal accepted, and it is needed when proposer asks prepare, and lower prepares anyway will be ignored. So the highest one, the highest proposal accepted. Second, he has to remember his last promise. So highest prepared, it has promised. It has promised to ignore accept with lower number. So these can be saved in a persistent store. And once the acceptor recovers, he uses this information to continue his algorithm. One more optimization. Paxos requires 2 round trips, the prepare phase and the accept phase. But if a value is chosen, we know that every high proposal chosen will have that value. So one possible optimization is that the proposer skips the accept phase if the majority of acceptors return the same value v. Then he knows that the value is chosen, and he knows that is the decided value. He can decide on that. Now, as we understand, just to look at the performance, the normal single value Paxos algorithm require 4 message delays or 2 round trips, 2 messages for the prepare phase, broadcast and get majority, and 2 messages for the accept phase. In many cases, and that will be explained well in part 2 of the course, is that only the accept phase is run. This is the case when all the proposals agree on one leader, and this leader is the one that is proposing. In that case, we will actually need only an accept phase because the leader is known a priori. We will understand this much better in the second part of the course, and in fact, you will not only be able to decide on an incremental sequence of values, but also to be able to pipeline these decisions. We will see this in the second course when we talk about sequence consensus.